Want to learn.
Alright, a couple things. I posted on yesterday, but I want to make sure that we do discuss it as a class. So, we'll start with a few tips that you want to think about when we deal with absolute value equations first. Okay? Start with absolute value equations first, and then go from there. By the end of the day, we'll have everything you need to know to complete that homework assignment, which I've moved back to. I haven't moved it yet, but I will. Moving back to Monday, so you can ask questions about some of those problems that you're going to kind of first encounter tonight. But yesterday we talked about if I have the absolute value of ax plus b is equal to c. Okay? We did two things for that. First thing we did is that we just basically got rid of the absolute value bars and solved that equation, right? Now the logic behind that is that this expression initially could be positive. Does that make sense? If I take the absolute value of 10, is that going to give me 10?
Yes.
Yeah. So, and it was positive 10 here, right? So I don't really care then about those absolute value bars if the expression in itself is positive. Okay? But we also know that this statement should be true as well. Negative 10, its absolute value, should also be positive 10, right? So the second thing we did yesterday is, and I'm going to write this a little bit different than we wrote it yesterday, is that saying that the expression itself can actually be the opposite of ax plus b. Does that kind of make sense? Instead of being 10, it could have been negative 10. But most generally speaking, it's just easier for us, instead of put the negative here, multiply both sides by that negative and put it over here. Does that kind of make sense to everybody? And just rewrite this as ax plus b equals the opposite of c. So that's why we do those two rules, is because we're interested in two situations. When that expression itself is actually a positive number, and that's going to give me this first case here, but also when that expression ends up being a negative quantity, and it'll give me this second expression, or second equation. And that, I think that was something that we shouldn't have too much of an issue with. The one thing I want you guys to realize, if I tell you, absolute value of 2x plus 5 is equal to negative 12, that's a no solution question, right? Because absolute value can never be a negative result, correct? And graphically, understand everything we do in this course can be taken back to a graph. What did I have? 2x plus 5 and negative 12. If I graph those two things together, remember we're always looking for the intersection. Do those two things intersect? No. Okay? So that's the logic behind why we simply can say automatically no solution. Because no matter where that red line is, as long as it's negative, they're never going to intersect, right? Okay? But once they become positive, then we do get some intersection points. So that was one thing we talked about yesterday. And that kind of led into the discussion of what we do when we have the absolute value of ax plus b is equal to some expression cx plus d. Okay? Notice the right-hand side does not have absolute value here. Okay? So the right-hand side, at least right now, where we're at in the textbook, these are both always going to be linear. Okay? But we approach this the same way. We're saying that this left-hand side, if that is positive, then it should equal that positive expression. Okay? So I'm saying ax plus b should equal cx plus d. Okay? Second case scenario is that this thing here could actually be a negative amount, but the absolute value of it should be equal to this positive amount, right? Just to maintain kind of a similar aspect as this one is, or was, we multiply the right-hand side by a negative here. So just to keep kind of the same rule, we'll multiply this right-hand side by a negative. And that will be the same thing as if we would multiply the left-hand side by a negative, right? Okay. The only thing that is a problem with this one is that you're going to get two solutions, right? Okay? At least that's what the algebra tells us we're going to get. But let's think about this. Let's say I give you the absolute value of 2x plus 5 is equal to trying to think of something that will be interesting here. Let's just go x minus 1. I don't know how interesting that's going to be, but first case scenario is to go 2x plus 5 equals x minus 1. Fairly simple, just get rid of the absolute value bars, right? Okay. The second scenario is to take 2x plus 5 and now set it equal to the opposite of this. So the opposite of x minus 1. And now solve it. So I'll have x, I'll move my 5 over and I'll get negative 6. Okay, over here, gives me 2x plus 5 equals the opposite of x plus 1. I'll add my x over, gives me 3x. Move my 5 over, gives me, what, negative 4. X is equal to negative 4/3, right? When you have this situation, this is a special case, and this was on the video I made yesterday after class. This is a special case because what we have going on here is an absolute value, okay, which is, that thing right there is going to look like that v, right, graphically. And cx plus d is going to be a line, correct? Well, some lines might not intersect that v at all. Some lines might intersect that v one time. Some lines might intersect that v 2 times. Does that make sense? The algebra we do is always going to get 2 solutions. But those 2 solutions might not even, neither of them may work, one of them might work, both of them might work. We got to check. And the logic here is when you go back to the beginning, okay, regardless of what this number here becomes, okay, that could be a positive amount or a negative amount. I don't really care. If I plug in 2x, so 2 times negative 12 plus 5 is negative 7, right? Okay, so I get negative 7 there. So what's the absolute value of negative 7? 7. So this side should evaluate to be 7, right? Well, what's negative 6 minus 1? Negative 7. So we just evaluated and said the absolute value of negative 7 should equal negative 7. And we know that that is what kind of statement? A false statement. So that solution does not really work. Okay? And it's because of that idea of what is happening in the background when we graph these, the intersections of these 2 things. Same thing here. Okay? Again, and I'm not going to evaluate this portion right here with this 4/3 because I know it's going to become probably a negative number, right? Or a positive. I don't really care. But when I take absolute value, the left-hand side should end up being positive, correct? Well, when I evaluate the right-hand side, what's a negative minus another negative? A bigger negative number, right? So I'm saying the absolute value of something should equal a negative number, and that's false as well, right? So that solution does not work. So really, the work that we did, both solutions don't really work, okay? And the logic behind that, if we graph this, the absolute value of 2x plus 5 and now x minus 1 is those 2 graphs, and obviously you see that they don't intersect, right? Okay. The closest point that they would intersect is around here, okay, but then they start to diverge even further and further away from one another as we move in that direction, okay? Now, we could take this line and start moving it up, and you see that maybe right there they intersect 1 time, right? Maybe right there, now they intersect twice, right? Okay? And I can start moving these. Okay, I'm always going to intersect, just the way this is set up, these 2 will always intersect twice. So x plus anything greater than, I guess, let's just say anything greater than 2.5 is always going to intersect twice. But let's say I change the slope a little bit. And let's go... let's make it a steeper slope, so... Oh, not that one. Now you see a situation where maybe they only intersect one time, right? And now as I zoom out, that red line is always going to be on the interior of that V. You'll only get one intersection. Or, obviously, maybe we can zoom out far enough, but we're still always going to intersect. Okay? So there's going to be situations where, if this kind of branch of the absolute value is, if its slope is equal to the slope of the red one, okay, or the slopes just vary so that they never intersect, we'll get 0 intersection points, okay, or 1 or 2. In this case, we're always going to get, because of the way the slopes interact with one another, we're always going to get at least 1 intersection point. But when we do the procedure algebraically, we don't necessarily know that right away, right? Until we look at the graph and think about the graph. So that's something to always think about as you're doing these problems. And that's only a special case with that being an expression on the right-hand side. Because if it's not an expression, if it's just like 5, zoom that real far. If it's just like 5, you're going to have a horizontal line, right? And you're going to get that V to intersect 2 times, okay? If it's 9.6, you're going to get that V to intersect 2 times. So no matter where that horizontal line is, you're going to get 2 intersections. Unless it's down here, and obviously we get none. But once we start to change the slope of that line, that horizontal line, then issues arise with the amount of intersection points we have, and the beginning format is going to look something like this when we start messing with that slope. Okay? So whenever you have absolute value equal to an expression, a variable expression, you got to check your answers. Okay? If you guys, I know you don't have to do this right now, but on your TIE 3s and E4s, if you want to graph, I don't know if you've seen this before in other courses, but if you want to graph absolute value, it's pretty easy on these. All you have to do is type in, go to your y equals, okay? Go hit the math key, and then you go over to the number option, NUM, and ABS is your first option there, absolute value. And then type in, we want 2x plus 5. Okay? And then maybe I go, let's just say 5. Go horizontal line there. And we can graph those. And now can we use that intersect tool under the calc options to find those x-intercepts? Well, not x-intercepts, but x values of their intersection points. So that's how you do absolute value on the calculator. If you ever have a question on the calculator and we haven't done something on it, don't hesitate to ask, is this possible? And if I know how to do it, I can show you that. Something that people forget, I forget this a lot, there's a lot of different functions on the calculator, and they're kind of hidden, kind of like that one was. You had to go through a couple buttons to get there. But if you know, hey, we're looking for ABS, if I hit the second button, and then the 0, that takes you to your catalog, and everything's alphabetical there. So if I'm looking for ABS, that is the first thing that comes up. But let's say that I'm looking for something that starts with R. I can go find my R key, push R, and it'll get me to that section. Does that make sense? And the catalog might be a little bit easier for you to kind of search through than finding all the functions where they're hidden behind certain numbers and stuff like that. Alright, so that was one special case that we got to talk about, and always think about as we're doing these problems. What I hope you guys start to realize in this course is that mathematically, you want to do a little bit of the same thing that you do when you read a book in English class. Okay, I read, a chapter in English class, and don't I just inherently think about, what could happen next, right? Okay, foreshadow a little bit. When you see a problem in math, that's what you want to do instantly. Okay, what is this thing going to provide me, and then how does that kind of force me to go one route or another? Okay, always want to foreshadow, think what the next step, what the current step you're doing is going to impact the next step. And don't be robotic and just say, oh, I've done this before, go through it, circle my answers, and go to the next one. Okay? Because you might get these special scenarios, special situations. If you're robotic, you're not really paying attention to that kind of stuff. The next one was something like this. I don't know if you guys asked about this, but this did come up in the first class. We'll have something like that. AX plus B equals CX plus D, both of them in absolute value bars. So I'll just give you a specific example. Let's say I have like 2x plus 1 equals absolute value of 5x plus, I don't know, let's go 10. All right. So graphically, those are two V's, right? Okay. Well, those two V's are probably going to intersect 2 times. Okay. If you graph those, I'm assuming that's probably what you get. But here's how we go algebraically and figure out this result. Okay. What we're going to do is that we're going to, just like any other time that we've dealt with absolute value, simply to get half our answer is that we just get rid of the absolute value bars and we solve the remaining equation. Okay? And the reason we do that is that we're thinking that this expression here with the absolute value is equal to that expression with the absolute value as long as the expressions that are underneath, as long as that thing right there and that thing right there are equal to one another. For instance, that's going to end up being a number, right? What if that number ends up being 22? Is the absolute value of 22 the same thing as the absolute value of 22? That's because 22 is equal to 22, right? Well, if 22 represents AX plus B, and 22 represents CX plus D, then we don't really need, because they're both positive, we don't really need to do anything with those absolute value bars. Does that make sense, everyone? Okay? But we also know, I'll do it with the right-hand side. If that's absolute value of 22, to get a true statement, this could be the absolute value of negative 22, right? That would still be a true statement. I take the absolute value of this, I get 22. Take the absolute value of this, I still get 22. So that tells me that this expression here could be AX plus B. But this one could be the opposite of CX plus D. Okay? So we get the concept, or we get the idea that this is going to be true. What I have written in blue is going to be true if the expressions inside the absolute value bars are in fact the same sign. They're both positive or they're both negative. Okay? If I put a if I multiply this red stuff by negative on both sides, don't I still do the same thing? Okay? So this first case here is assuming that these two expressions are the same exact sign in regards to one another. Both positive 22 or both negative 22 or something like that. Okay? This black one is saying that this expression, AX plus B, is an opposite signed expression to the CX plus D. But whenever I take opposite signs, okay, and take the absolute value of both sides, I still get the same result, right? I still get a true statement. All right? So that's the logic, that's the reason why we still do these two steps. So over there then, you'd have 2x plus 1 equals 5x plus 10. That'd be your first scenario. Your second scenario would be 2x plus 1 equals the opposite of 5x plus 10. I'm going to leave it for you from there to go and solve those. But that will give you two locations in regards to the x values where those two graphs intersect. Okay. I really want you guys to understand the thing, especially if you think we spent a lot of time on this, and maybe in Algebra 2 you did this, but in Algebra 2 I'm thinking maybe you didn't try to see all the things that were going on in regards to the graphs and the understanding. I think in Algebra 2, and it's because of the standards and stuff like that, that we force ourselves to kind of learn the process, learn the basic arithmetic, the analytical approach, and just be that robotic person that goes through and does the problems. In this class, I want to get deeper into that kind of stuff and think about why those things work. Okay, it wasn't until I was in high school. I was that person that wanted I wanted the process so I could do the steps. I had to be shown, do the steps, do the steps, do the steps, and then I could perform on a test or a quiz. But once things changed a little bit, I didn't really have the skills to adapt to those questions. It wasn't until I got to college and I had a professor who said, "Don't try to memorize things in math. Okay, don't be that robotic person. Okay, try to develop relationships. Try to develop an understanding of what's going on in the background. Okay, because there's multiple approaches. There's graphical approaches, analytical approaches, that kind of stuff. And understand the dynamics of all those, and then you don't have to memorize anything. Okay, you just understand the intertwining of the mathematics system, and it makes things so much easier. So that's hopefully what we kind of accomplished this year. Whether that slows us down in regards to the amount of material we learn, I'm okay with that because I'd rather have the payoff of understanding in great detail a small chunk of mathematics than having no understanding of a lot of mathematics. Does that make sense? Okay. So that is the several situations that we deal with in regards to equations. Now, every time that we come across a topic in, allergies are killing me. Every time we come across a topic in this class, we're going to solve. First thing we'll do, and we'll introduce this tomorrow, but we'll introduce what we call functions. And pretty much every chapter is going to introduce a new type of function. Okay. Later in that chapter, then we start taking that function and setting it inside equations. So we start solving equations. So maybe in chapter 4, we'll talk about logarithmic functions. Later in that chapter, we'll say, okay, now let's solve logarithmic equations. Okay? And then later in that chapter, we'll say, okay, let's solve logarithmic inequalities. Does that make sense? Okay? So as we go through the course, every chapter is going to be basically, here's a function, here's equations with that function, and now here's inequalities with that function. Okay? And then we go to the next chapter, and here's a new function, here are equations with that function, here are inequalities with that function. Okay? So it's a good idea to understand what we're saying with inequalities and what they mean to us graphically. If you have an inequality, let's just say we're starting with, let's just start with something really basic. If I had, there's 2x plus 3 and x minus 2. Okay? I've got those two graphs, okay? And I want to know where those two things are equal. And we spent a lot of time in Algebra 1 finding that location of -5, -7, where those two things were equal, right? Systems equations. Now that we know where they're equal, we should automatically know then where they are unequal, right? They're unequal everywhere else. Does that make sense? Okay? But now the question is, how are they unequal? Okay? So let's just say, take for example, if I say 2x plus 3, which is the red one, orange one, whatever color that is, and x minus 2, and I write it that way. And I say, I want to find out where 2x plus 3 is less than x minus 2. Well, graphically, we're thinking then, where are the y values for this one? Now let's write it this way. It's kind of a long phrase, but for what x values? So our answer is going to be in regards to x values. Okay? So for what x values are these y values smaller than these y values. Okay? So our solution is, if we have 2x plus 3 is less than x minus 2, we're going to ask ourselves for what x values overall are these y values here that go with the 2x plus 3, are they smaller than the y values that go with x minus 2? Okay? So we know where they're equal. We know where the y values are equal. They're equal here at -5, -7, right? And we would circle -5 as our answer for x. Okay? Now, if I want to say, where is 2x plus 3? Where is that less than x minus 2? Well, if I start looking at some x values here, okay, let's say that we turn this on. Okay, if I'm looking at 2x plus 3, which is this orange curve here, okay, orange line, okay, and I look at maybe an x value of negative 8, okay, x value of negative 8 would be that line right there, right, okay. If I look at the y value of the purple one has a y value of negative 10, right, okay, and the purple one is this one, okay. The y value of the orange one is about probably negative 13, right? Okay. Well, is negative 13 less than negative 10? Do you guys agree with that? Yeah? Okay. So it is.
Alright, the camera stopped after the last video, so I'm going to pick up where we were and then get back to the class lecture. But we were talking about, when the camera stopped, that this inequality, what we're asking about, what we're thinking about graphically, is that when is the red 2x plus 3, and I guess over here it's orange, but when is that graph less than x minus 2? And we're really interested in asking the question, for what x values are the red or orange y values below or less than the blue y values? So we start to see over here, graphically, now if I just pick a point like x being negative 8, we see that the red ones or the orange ones are less than the blue ones. Okay, so y value of negative 13 is less than a y value of negative 10. Okay, so hopefully you recognize and you can argue that in all of that picture there, you would agree that the orange ones are below the blue ones. Okay, so then we have to identify what range of values that is, what x values that exists for, and they're the x values from negative infinity up to negative 5, because negative 5 is where they become equal. Okay, so if I know where they're equal, I should know where they're unequal. Okay, they're unequal to the left of negative 5 and unequal to the right of negative 5, but then we just have to determine how are they unequal, which one's greater, which one's less than. So everything we do in this course, when we talk about some type of equation, we eventually talk about an inequality as well, and that's the concept that we're thinking about. Okay, now pick up with what we're doing specifically in class is dealing with absolute value. So our question is, when is the red absolute value 2x plus 6, when is that below 4? Hopefully you guys can argue that, and we're asking for what x values is this red one below 4, and hopefully you can argue that between negative 5 to negative 1, those are the x values where the red one is underneath or below the blue one. All right. So what we're going to do is kind of develop a rule here to help us algebraically figure out what that range of values is. So I'm going to start with an arbitrary ax plus b is less than c. And I'm just going to think about just a general one-dimensional number line first. What this is saying is if we've got a 0 here, okay, this expression should be less than c units away from 0. Ax plus b, when I find x, plug it back in here, that x value is going to force ax plus b to be less than c from 0. So less than c, I'm looking for x values that plugging in there will give me something. Ax plus b will be somewhere inside that interval. But we also know that anything over here can also be less than c units from 0. So we're looking at basically that line segment. So the way we find that is we say, well, our expression has to be between negative c and positive c. So that's why we come up with the idea that if I have absolute value of ax plus b is less than c, we rewrite it as the opposite of c is less than ax plus b is less than c. And we just go through and we solve that. So for our particular problem here, we would rewrite this as negative 4, take the opposite of that, a less than sign, now our 2x plus 6, and then positive 4. We'll go through and solve that. We talked about in class that if you just had that, you would subtract 6 both or first, and if you had just that, you would subtract 6 to solve for x first. So if we got them both at the same time, let's just solve both the inequalities at the same time. So we'll subtract 6 from all three sides, or three parts. Get negative 10 less than 2x is less than negative 2. And then again, for the same reason, if we just had that, we'd divide by 2. And if we just had that, we would divide by 2. So just take care of all at once. Divide everything by 2. And we get negative 5 is less than x is less than negative 1. And that was remember that's set notation. We're going to write this as interval notation, negative 5 and negative 1. And that's what we're developing here. Now my hope is that you realize that we know where they're equal. They were equal at negative 5 and negative 1. And that would have been solving the equation absolute value of 2x plus 6 is equal to 4. We've now solved 2x plus 6 is less than 4. So where can we say that absolute value of 2x plus 6 is greater than 4? Well, the place that we say it's greater than 4, if we know where it's equal to 4, and we know where it's less than 4, we should, so that eliminates all of these. We've already taken care of those things. Now, doesn't it make sense then that this is the regions here, the stuff here in yellow would be the regions where they are greater than 4? Okay. So that's the whole idea. There's three components. There's equality, there's less, and there's greater than. If you can find two of those, you should by default know the third one. Now, we're not always going to be asked to find all three, so we should have an approach that if I'm just asked to find greater, then I can find that directly. And here's the idea. If I have the absolute value of ax plus b is greater than c on a number line again, if 0 is here, c is there, negative c is there, we're looking for an x value that puts my expression ax plus b bigger than c. Okay? But a value over here would also be more than c units from 0. Okay, so any values over here are also more than c units from 0. So that gets these rules. So ax plus b is greater than c would give me this stuff here. And that's pretty direct, pretty easy, I think, to see. But now to get these things over here, we're going to take ax plus b, and we're going to say they have to be less than negative c. And those are the two components that you need for a greater than inequality. And we write the word or in between. Okay, so let's see how that kind of relates to the picture over here when we go and do this particular problem. If I have 2x plus 6 is greater than 4, I'm going to do that. 2x plus 6 is greater than 4. But then I'm going to write the word or, and I'm going to do 2x plus 6 is now less than negative 4. Subtract 6 from both sides, I get 2x is greater than negative 2, x is greater than negative 1. Or, now solve this one, 2x is less than negative 10, x is less than negative 5. And now, these are in set notation. We put them in interval notation. So x is greater than negative 1. So those are the values that are greater than negative 1. Or x is less than negative 5. So negative infinity up to negative 5 are those values. And now we want to make this a number line. So what we're going to do is we're going to put that first, and we're going to put that second, and we're going to union them. And that means then we've got a number line in chronological order. That's the largest negative number, next largest negative number, or I guess a negative number closer to 0, yet another negative number closer to 0, and then we start getting our positive number. So this should be left to right in order as you would see them on a number line. And that's exactly what we're seeing over here. We've asked ourselves, where is the red curve above the blue curve? Where is the red one above the blue? When is 2x plus 6 above 4? And we're seeing that at negative 5 in that way. So negative 5, negative 6, negative 7, negative 8. Okay, those values, the red is above blue. And then over here at negative 1 and to the right, we're getting the red one above the blue one again. Okay. So that's how you're going to approach those absolute inequalities.
All right. We could take 2x plus 6 is greater than 4, but knowing then that this is where they were less than one another, knowing that at -5 and -1, that's where they were equal to one another, should I be able to interpret the rest of the number line as where they're unequal to one another? In the fashion of being greater than? Does that kind of make sense? Okay. It's the complement idea. If I know I've got basically three regions. I've got equality, I've got less than, and if I know where those two regions are, I automatically know the default third region of greater than. Does that make sense to everybody? Okay. And you might see that in WebAssign. I know when we had Math Excel will do that. They give you three options or three parts of the question, and they say find out where they're equal. And the next question was find out where they're less than. Well, then the third problem, you don't have to do anything because you know where they're equal, you know where they're less than. Everywhere else on my number line is where they're greater than. Does that make sense? Okay. So here we should be able to say from -infinity up to -5, and from -1 all the way to positive infinity is where the orange one is greater than 4, right? Okay. Let's go through the algebra and see how we can replicate that. Just generally speaking, when we have like an ax plus b is greater than c now, okay? Going back just to a linear, one-dimensional number line here, okay? If I start, the zeros here, let's say c is there, let's say -c is there. If ax plus b is greater than c units from 0, that expression is greater than c units from 0. So I'd be looking at something that looks like that, right? Okay? Ax plus b is greater than c units from 0. And that would just be simply finding that set of solutions, would just be taking ax plus b greater than c and solving that inequality. Okay? But if I'm over here, isn't that distance there greater than c units away from 0 as well? Yeah. Okay? So we'd actually have to figure out how we can incorporate those. Okay? Well, graphically speaking, if I want to take that graph and translate it into an algebraic expression, these values are less than -c, aren't they? So we're going to write ax plus b is less than -c. Okay? And those are the two things that we come up with. We write the word or with them. But those are the two inequalities that we come up with to solve a greater than question for absolute value. Okay? One thing, I don't know if I mentioned this, whenever you're doing absolute value, if I have 4 is less than absolute value of 2x plus 6, I write it that way. I want to read it from the absolute value first. Does that make sense? So I read it, absolute value of 2x plus 6 is greater than 4, because then it gives me this rule. Alright? I don't want to read it as 4 is less than, because then people are going to get stuck, and they're going to do this, which is incorrect. Does that make sense? Okay? You've got to read it from the absolute value first, and then to the constant. Okay? So, looking at this one, we're going to come up with 2x plus 6 is greater than 4. Do a little bit of work there. And then we're at 2x plus 6. Okay, this rule is saying flip the inequality symbol. Goes the opposite direction, so now we're trying to find these solutions that are here. And then you take the c value and make it negative. So, negative. Now you just solve those two inequalities. 2x is greater than -2, x is greater than -1. And then here, 2x is less than -10, x is less than -5. And that's what we got here, right? That's what we kind of anticipated having, is at that point right there is -1. Then to the left of that is where the orange line was above the blue one, okay? And that is infinity up to -5. And then that value there is 1. That direction from -1 to positive infinity is another place where the blue one, the orange one is above the blue one. Okay? Now when we write our answers, we want our answers in interval notation, right? So x is greater than -1. How would I write that? If I'm thinking about a number line, I'm thinking about numbers that are greater than -1. What would be the first number you come across left to right? -1, right? Okay? If I'm thinking about something like this, right now we're saying we've got -1 right there. And we want numbers that are greater than that. Well, we want to identify in interval notation that red ray? Well, it starts at -1, and it's going to go to what? Infinity. Okay? Now this one here, x is less than -5. So if this is -5 over here, we want to identify an interval notation, that ray. So what number do I start with? -infinity, right? That's the first number I come across, all the way to the left. And what would be the last number you come across on that ray? -5. Okay. So, still not done though. Because we want to make sure that we understand when we have the word or, I erased it, but that word or means union, right? That means you got to stick your two solutions together. Alright? So we got to tell everybody that these could be answers, or these are answers. Okay? So any point that shows up on here is an answer, or any point that shows up over here is an answer as well. Okay? So we got to put those together. And now when we put these two things together, we want to make sure that they're in chronological order. They represent a number line. So what is the furthest, the number that is furthest to the left in these two things here? -infinity. So that one comes first. Union then, -1 to infinity. And that should mimic then the number line that we have, that we're looking at. Is that doable? Okay. When you're working on this stuff, my suggestion, at least early on, every time that you come across one of these inequalities, okay, something that's safe to do is to first rewrite it so the inequality comes first. Okay, so if I had like 13 is greater than absolute value of 2x plus 5. Okay, I'm going to use my symmetric property of equations and inequalities, and I'm going to rewrite that as absolute value of 2x plus 5. Now, that absolute value bar, it's pointing, if that was an arrow, it's pointing to the 2x plus 5, right? So it's still got to point to the 2x plus 5. And then I had my 13. And now that helps me use the correct rule that I'm going to basically do this. 2x plus 5 less than 13. And I'll put in the -13 over here. Okay? I think that's the safest thing to do. People get themselves in trouble when they leave it this way. And professors, people that write standardized tests, college entrance exams, whatever, know that people are going to get themselves in trouble when they do this. So it's inevitable that you'll see something like this on tests. Does that make sense? Let me ask this question. You told me if I take absolute value of 2x plus 10 is equal to -15. You told me what about that? It's impossible. No solutions, right? Okay. Absolute value can never be negative. So what if I do this? When is the absolute value less than 0? Never, right? Because absolute value less than 0, we're saying that it has to be a negative number, right? Well, absolute value can never be a negative number, so there's no solution there. Even if I get like a -10 there, no solution there, right? Okay. What if I ask you this question? 2x plus 10, when is that greater than -10? Think about this graphically. 2x plus 10 is going to look, let me do a little bit of work here. 2x plus 5, so it'll be 1, 2, 3, 4, 5. It'll be like that. Slopes are kind of jacked up there. And -10 is going to be down there. When is this v above -10? It's always above it, isn't it? So what x values would that be? Be all of them. Be all real numbers, right? Negative infinity to positive infinity. Okay? So there are some times, and you go through the math and do all the math analytically, you'll get the same result. But there are times when looking at a question, doing a little bit of analyzing that question before I just start randomly writing stuff down. Okay? Do that foreshadowing and think, what are we really asking here? Okay? When is an absolute value less than a negative number? Absolute value can never be less than a negative number. Okay? When am I asking absolute value to be greater than a negative number? Well, absolute value is always positive. Positive numbers are always greater than negative numbers. So that's always. Okay? So keep those things in mind. Those are going to help you as you move on. I think, Callie, you had a question yesterday. Was like absolute value of x is less than like 8 and less than 10, something like that, right? Now it's a between statement, and every between statement is really two statements wrapped up, right? Okay, inside it, it's a little bit different. If it was just this, okay, and maybe like x plus 2, we would solve that all together at once, right? But if it's absolute value, we want to treat it a little bit differently, and we want to treat it as individual between statements, okay, or just individual inequalities. So I'm going to rewrite this as absolute value of x is less than 10. And now I'm going to rewrite it as absolute value of x is greater than 8. Does that make sense? Okay. Now because it's a between statement, I'm going to rewrite it this way. I still need the betweenness or the and or the intersection idea. Does that make sense? Okay. And that and section takes precedent over any other operations that we come in a moment. So order of operations, that's kind of most important here in a moment. If you have absolute value like this, if it's a less than, don't you do this? Right? Now, and, that takes precedence. You got greater than. Doesn't greater than become x is greater than 8 or x is less than negative 8? That make sense to everybody? Okay. So what we're going to do is we're going to look at graphing that and graphing that. Okay. We're going to do it all together, but then we're going to look at this and that, and meaning intersection, meaning where they overlap. Okay? If I graph that, I'll finish this on the smartboard. Have a great rest of the day. Make sure you look at that assignment so you can ask.
Okay, so the bell rang again. Someone finished this question. We talked about, I think these were the numbers we're using. If not, it's the same idea. With a between statement like this, we would normally just leave it this way, and whatever this expression was, we'd solve for it, solve it to all, or do the opposite operations to all three parts. But with inequalities, including absolute value like this, you want to treat them a little bit differently. We're basically going to rewrite that first. Okay, so I'm going to rewrite, you want to write absolute value first. So absolute value of x is greater than 8. Okay, then I'm going to rewrite that to where it says absolute value of x is less than 10. Okay, and understanding that this whole thing was a between statement. And between means intersection or the word and. So I'm going to put and in here. Okay. So when I'm done, our solution should have this criteria and that criteria. Now, talking about what we did today, we have absolute value greater than 8. That actually meant that we had to go absolute value of x is greater than 8, or x is less than negative 8. I gave the two results. That, and if I put a number that's bigger than 8, like 12 in here, 12, absolute value of 12 is 12, greater than 8. That's true. But if I put negative 12 in, which is what this is saying, negative 12 should be in that range. Absolute value of negative 12 is bigger than 8. So, okay. So that's what that breaks down to, those two inequalities. Still got the word and in here. This breaks down to two inequalities as well. We just write it this way. Negative 10 is less than x is less than 10. Okay? So our final production here has to have this and that idea. So what I'm going to do is I'm going to graph both those concepts. I'm going to graph this one, x is greater than 8, or x is less than negative 8. So that would, if 0 is here, let's put negative 8 there, let's put 8 there. If I were to graph those, x being greater than 8 would be those quantities. Less than negative 8 would be those quantities. Okay. Now, this stuff here, negative 10 to 10, if I plug those in, let's do some blue, negative 10, positive 10. What that's saying is that x is those values. Okay? But we want x values that have this criteria and that criteria. So graphically, that's where these two things overlap, and that's going to be those values there and those values there. So how do we write that in interval notation? Those purple values go from negative 10 to negative, for some reason that thing wants to keep coming back, negative 10 to negative 8, and then over here 8 to 10, and we'll union those. Okay, think about any number that you take out of that interval should be able to be plugged in right there and should satisfy that condition. Okay, if I plug in 9, 8 is less than 9, and 9 is less than 10. 9.5, 8 is less than 9.5, 9.5 is less than 10. I should also be able to put in something like negative 8.5. Okay, 8 is less than absolute value of negative 8.5, which is 8.5. So 8 is less than 8.5, which is less than 10. So that makes sense. So these values, I think these were probably pretty obvious that those should be part of our solution. But these, maybe not so obvious. And that's what this process will provide, is the addition of these. Now you do the exact same thing. If I had like 8 is less than absolute value of x plus 2, less than 10. I just now have something I have to solve for in those two things and solve for in that one. Makes it a little bit harder, but in the end, you'll get down to something like this. Your results are not going to be, these kind of mirror each other. Negative 10, negative 8, 8, 10, same numbers, different signs. Won't happen here, but you'll get something similar.